A quick request. This is going to be a Blackboard talk. So I'm hoping everyone can actually, we'll try to fill in the first 3 rows as much as possible. So please.
Like good students.
Can you please move to the front row? There's plenty of seats here. Perfect. I think that. There are seats here. This is a Blackboard presentation, so it's there's 2 seats here.
Ready? Okay, welcome back. Good morning. All right, so it's a pleasure to welcome Pramod Viswanath to our IT school. So Pramod is a graduate of UC Berkeley, under Undirected advisor, the big man himself, as I say. We received some awards at UC Berkeley, the jury award for research in IT systems, the Friedman Prize for research in applied mathematics in the math department. He returned from Berkeley, spent a year at Clarion, now part of Qualcomm, doing Dr. Richardson works. He started at UIC in 2001, and he's now a full professor there. He's the author of a textbook on wireless communications. I use definite articles in public, so it was a textbook on wireless communications, wide wave plumbing textbook on wireless communication, authored with David Shea, and also worked on source coding, multiple encoder and multiple description. So his talk today is going to tie together many of these themes: wireless communications, EE systems, applied math. We'll link it all together. I guess there's no source coding. Okay, so that's the point of this agreement. It's also the first chalk talk of the school. So join me welcoming Pramod to our school.
Thank you. Okay, good morning. Still several people coming in. I hope the board is really visible from that far out. We'll see what we can do. I'll also try to give out my notes at the end of this. The organizers can post them online. Okay, let's get started. It's a 3-hour thing. So we'll try to break it into sort of 3 different lectures, and we'll give breaks in between. These 3 lectures are on, I just want to make sure. So we look at networks, which is a pretty loaded word. And we'll look at both, you mentioned I should use...
You want to be seen in back.
That's right. Sorry. both wireless, and the real goal is to sort of think about communication on them. So this is pretty much all of network information theory and network communication, and we only have a few hours. So we try to focus on, I would say even classical work on networks, on wireline networks. And once we get, I think they're widely taught and understood in other communities, particularly in the theoretical computer science community, not so much in the not so much at all in the information theory community. I've enjoyed learning them and participating in them. So we'll spend a little bit, and I think it helps tremendously in understanding the far more complicated wireless networks. So you could say we'll build some muscle, get to know wireless networks better, and that will help us build both models and also understand more of wireless networks. Okay, that's the broad outline of the talk. Wireline networks are easy mathematically to write down and define. So a wireless network is a graph, set of vertices and edges between them. And for this talk, we'll look at both directed graphs. That means the edges have directions, or undirected graphs, where the edge doesn't really have a direction. They're both studied widely within the context of graphs and wireline networks. And when it comes to wireless, we'll probably have a lot more to say which ones to pick and not, or which ones to prefer. I'm also going to think of capacitated graphs. By that I mean there are numbers called capacities on certain elements of the graph. In particular, of particular interest to get started is the so-called edge capacitated graphs. So that means for every edge E in the edge set, we associate a capacity, which is basically a non-negative number on that edge. So let's call it C of E. Capacities are non-negative. I mean, this is not to be confused clearly by the operational meanings of reliable communication, capacity, and so forth. So these are more informal notions of capacity. There are other types of capacities, and we'll see some of them as we go along in these lectures. I'll just say one more here, though we won't get to it until the last part of the lectures, which is to do with node capacities. Node capacities have, for every vertex or every node in the graph, you have a capacity associated with that vertex. Well, what do these capacities mean, or what role do they serve? Well, that's the whole point of communication. Well, I guess I have to give some operational problem, and then we can talk about the role of capacities. And I'm interested in communication. Communication means certain nodes are called sources. Let's call them S1 through Sk. And certain nodes are called destinations. Let's call them T1 through Tk. The K is the same, and it's kind of on purpose. The point is, at least there is a specific type of communication. Now, eraser is right here. I mean, this is so broad, so we're going to focus on something very specific in this talk, so I'm trying to get the setting right. The point to think of in communication is that these sources have some messages or some data associated with them, and they are at those nodes, and the corresponding destinations want these messages. When k equal to 1, so this is the so-called multiple. So let me first do k equal to 1. That's the simplest setting. Such a setting is called Unicast. Just one source communicating with one destination over this graph. You could, except subject to some constraints, and the constraints are through the capacities on the edges. For k more than 1, it's the so-called multiple unicast setting. So there are pairs of source, there are source destination pairs, and there are multiple of them. And the point of, so maybe I can even ask a question. So I'm sure you've all heard of this thing called multicast. How is this related or different from multiple unicast?
One source may send to multiple destinations and not separate source destination pairs, I think.
Well, all these sources could have been at the same node. Would that become multicast?
Because everyone wants to decode exactly the same.
Okay. So multicast refers to, there's no way I can get to names anymore here. I'll try, but that's going to be hard. This is too big an audience for that. Multicast refers to the fact that all the destinations are interested in a common message. So multicast typically refers to a single source. That we can handle here by having all the sources to be the same vertex. There was no restriction one way or the other. But the restriction here was that each source had an independent message. That means the data they had weren't related to each other informally. Mathematically, they're just independent random variables. Whereas in multicast, they have just one single data that all the destinations want. So this is, you could say, is a common message in the parlance of information theory. And that's not something we'll talk about. Multicast is something fairly well understood and widely studied in the context of wireline networks, and also wireless, actually. Network coding, linear network coding, fair amount of understanding is there, and multicast is really a well understood problem, fairly well understood problem. Much harder, unicast is also fairly well understood, and we'll talk about it in these meetings. Multiple unicast is the more harder problem. This is the so-called network information theory issue where you have S1 talking to T1 with its own data, and S2 talking to T2, and the two source destination pairs really compete. Because the data are not related to each other at all, and it's not clear how it's really one is an interference to the other. Multicast is not so obvious because the destinations want the same message, so it could make sense. So there's no real competition as such. So the whole point of this multiple unicast is to resolve this tension, how to do the right thing, how to resolve this trade-off between one source talking to its destination, another source talking to its destination, sharing the same resource. Wireline networks are graphs, so they're much more simple and concrete to work with. Wireless is really a construction zone. So many things going on. And so we'll have to go slowly, kind of tread our way. So we'll work towards it. Any questions on this? This is really the setting of this of these talks. So in the first part of, I keep missing my razor. So okay, let me first set up what the problem then is. This is really an information theory summer school. So we are used to understanding what the operational problem here is, even without me being very formal here. I could be formal. So the setup here is, so this is a classical communication problem. Each of these sources have messages W1 through WK associated with them. And you want to think of encoding, decoding maps on this graph. So you should think of this graph as giving you, the directed or undirected graphs as giving you channels, except they are deterministic, noiseless channels. And you can even think of this capacity as giving you maybe an alphabet. And the cardinality of the alphabet is dictated by the capacity on the edge. So you can even think of them as inducing certain capacities as inducing certain deterministic channels, and you're really communicating on this network. The real question is what's the capacity or the capacity region of, so the question is the capacity region of multiple unicast. Turns out there's no punchline, definitely not during this talk, and it's not because we don't have time, it's because it's not quite known. So this is one of the open problems, easily stated, even with wireline networks. So the answer really is that it's open in general, but substantial things are known. So it's not like we completely throw up our hands. Quite a bit is known. And the goal of these few hours, is to get to know some of these results at a course level and also at some detailed level. So that's the purpose of the Blackboard talk. Okay, that's really the goal. And that will be the goal of the first 2 lectures. And the last lecture will do something more beyond these kind of capacities, and we'll get to wireless. So there are really 3 lectures. Lecture 1, we'll look at Unicast, where actually everything is known, both for directed and undirected graphs. In lecture 2, we'll look at what multiple unicast, how one might extend the understandings from unicast towards multiple unicast. We won't have as crisp an answer as in unicast, but we'll develop some quite a bit of the machinery. If the unicast is solved in the right way, quite a bit of the machinery can be directly adapted. So we'll do that. And lecture 3, we'll look at more complicated or more general, definitely more general, strictly more general capacitated graphs. These are so-called polymatroidal graphs or polymatroidal networks. Why we might want to do that is something I'll try to allude to. 3 years is not quite enough to build a full mathematical justification for it, but I think it will be reasonably easy to see some intuition towards it based on wireless networks. You could even view polymatroidal networks as some kind of a surrogate for wireless networks. So that'll be one of the main theses of that part of the lecture, and that will also help us sort of conclude the 3 lectures. That's the synopsis for this morning. Any questions? Do you see where we are, what we are doing? Clear? Okay. For lecture 1, for Unicast, turns out we can do both directed and undirected, without really any issue. Both of them are fairly well understood. They're a little different, but within the class of Unicast, they're very well understood. For multiple Unicast, things go horribly different, and will primarily focus on undirected. Part of the problem is that directed is really not understood, or maybe it's understood to be hard. Maybe that's the right way to say it. Yeah. There's a bit of understanding, but they're all more of the hardness type things. That means they're hard to understand. And when we come to lecture 3, we'll try to look at both directed and undirected. And undirected are more natural for polymetroid. Well, graphs, you can talk of directed or undirected, and wireless, we don't know what they are. They're not graphs to begin with. So we'll spend some time in lecture 3 motivating that. Okay, let's get started. This is lecture 1. So let's start off with, this is just plain Unicast. So there's just one of the sources of this graph, one of the nodes of this graph is called a source, and another special node is denominated as a destination. All the others, you can think of them as relays, all the other nodes. And we are interested in the maximum rate of reliable communication from the source to the destination using the relays. It's really a relay network with different edges and capacities on the edges. The idea of the capacity on the edge is that that's the amount of information that can flow on that edge. So you understand it loosely, and I think I'll leave it that way. Because these are deterministic networks, and we can think of them as just sort of bit pipes. That's what networks are. So you can also think of a natural achievable strategy. And that's called flow or routing. The idea is that source to source has something to say to the destination. There's only one source, one destination. Well, you divide up your information into tiny bits, tiny pieces, like a liquid, and you just let it flow from the source to destination such that if you look at any, several things happen. One, two different flows don't sort of interact with each other, don't interfere with each other. They can't add or anything. They just add on. They don't mix with each other. And for a given edge, the maximum flow on it is bounded by the data rate on that edge. So that's called flow. We'll be mathematically precise very soon, but I hope you have some idea what flow is. If not, we'll be very clear. Let's do that. Let's be clear. What is the how do you understand this as a? And I guess you want to look for the maximal flow, the best possible flow, that gives you the largest rate between S and T. What's a flow? I guess you look at all the paths between S and T. So script P. So lowercase p is a path from S to T. If it's a directed graph, then it's a directed sequence of edges. If it's an undirected graph, it's just a sequence of edges. So you understand what a path is. Path is, so here is S, here is T, so here's node V1, V2. This is, if these are edges in the graph, then this is a path. So path P is made up of SV1, V1, V2, V2T. It's a collection of edges. It's an ordered collection of edges such that the tail of the edge is equal to the head of the next edge and so forth. the next edge and so forth. Yeah. So it's called a path. Okay. So I think it should also be clear what paths are. And script P is just the set of all paths. I just write down S to T because this is the set of all paths that start with S and end with T. Right now there's only one S and one T, so it's kind of superfluous. But having this notation helps us when we have more S's and more T's. So look at all these collection of paths, and flow is something that goes along. When I say something, some information that goes or flows along these paths. The only thing that you have control over is how much information or how much flow to put on which path. Presumably some paths are not so good because they go through probably bottleneck links. Then you probably don't want to put too much, or you can't put too much on them. So you can associate, well, I guess flow is F. So let's associate F as the flow, and you have one such number for each path. And you can sum over all the paths because that's the total flow, total information. So you can say this is the flow, such that, of course, you can't, these are non-negative numbers. So we would like to maximize this over all possible FPs, such that flows are, you're sending some non-negative information. So that's there. And what else is there? Conservation at each. Yeah, so several ways of doing it. One way is that it's conservation at each edge. The capacity should not be exceeded. So if, in other words, for every edge in E, you make sure, so if you sum up all the F's over the paths P such that the edge of interest is in that path, then this should be less than C of E. Thank you. Exactly. Exactly. So this is called the maximum flow or the maximum routing rate of communication from S to T. It's a scheme, and it's a reasonably natural one on a graph. When I say natural, what I mean to say is that this is an optimization program. It's in fact a linear program, right? It's a linear objective function and linear constraints. So it's a linear program. At this point, the way it's written, it might look a little complicated because the number of paths is exponential in the size of the graph. So it might look a pretty big linear program, something that's exponential even to represent and maybe even to run in the size of the graph. Turns out there are alternative representations where it's polynomial in the size of the graph. We won't spend too much time discussing I'll spend a little bit here and there discussing the computational complexity of solving these linear programs. So I will mention it, but more on the side. We won't get too carried away with it. If you have questions, you should always ask. Yes.
Are we allowed to have passes that in them nodes are repeating?
Yeah, you can feel free. It's probably not interesting to have such things, but yeah.
Even in the undirected case?
Sure. No harm. No harm. It's probably not. They won't show up in this thing. No point in going around in cycles, but you'll just be using up the capacity for no reason. Mm-hmm. So it won't show up, but no harm in having them. Yes?
Can you restate the concept of mixing which you were pointing out?
Well, what I mean to say is that there could be schemes which are not flow. That's all I wanted to say. I mean, network coding is a good example of things where things get mixed up. A node gets different things, and what you send out is some mixture of them. Whereas with a flow, you'll never do such a thing. What comes in goes out in some other way through the edge without sort of without any real change. That's why I said this is a scheme. There could be other schemes. The main result in Unicast, so this is very classical, well over 6 decades, is that this is the right scheme, whether the graph is directed or undirected. So that's the classical result. There are several ways of seeing it, but there is a somewhat modern way, and we'll try to see that in this lecture. And this modern way really is rightly suited when we want to go to multiple unicast. That's really why we will do this. So the main result in this business is that max flow, by the way, this is max flow, is equal to the capacity. And when I write this word capacity, and when I say it, I mean the operational meaning of information theoretic capacity. That is the scheme, the right scheme. I said it's a scheme, but it also turns out to be the scheme. So that's the result for Unicast. And this is true whether the graph is directed or undirected. Oh, I never defined what an undirected graph was. Undirected graph is just really, you should think of it as a collection of directed graphs with edges on both directions between a pair of nodes. It's just that you can put any capacity on the two directions as long as the sum of the capacities is less than C of E. I mean, yeah, I was assuming you kind of know what an undirected graph was. So that's what an undirected graph is, as opposed to just a directed graph. So it's really a collection of directed graphs which have the property that the sum of the capacities of for any pair of nodes UV, the sum of the capacities from U to V and V to U is always C of E, the edge there. So that's what, so they're always the same over the entire collection of graphs. So it's really a collection of directed graphs. So when I talk of capacity of an undirected graph or communicating over an undirected graph, you also have the extra freedom of picking which directed graph to work with. Okay, so when I say max flow is the capacity, what I mean is there exists a choice of directed graph on which you do a flow, and that is the right scheme. Okay. So there's a modern way of seeing this result, and we'll try to do it. There's a reason why I wrote it as a linear program, and we'll try to use properties of linear programs. Any questions so far? It's clear? Okay. So this was an achievable strategy. Well, we need something else to show that we need some other strategy, or we need a bound on all possible strategies. And then we can compare these two things. And if they match, right, bingo, we are in good shape. So that's the way to do it. So we also want, I guess, what I would call an outer bound. Which would be an upper bound. I guess outer is more appropriate when you have multiple unicasts, but then let me use it, or upper bound. And this should bound flows or achievable strategies, or whichever. Is the question? Yeah.
This is also undirected and directed for unicast. So you said we can put edges in both directions, so such that the sum of the capacity will be exactly the capacity that we are looking for. So one way of choosing it is like 0 on one direction.
Yeah, you can do that, yeah.
So then you are claiming for directed or undirected, the maximum flow is the same if we choose an arbitrary direction for it.
No, I didn't say that. They're just separate problems. Directed and undirected are really separate, quite separate. Directed is more general. Mm-hmm. If you can solve a directed graph problem, chances are you have a good idea what the undirected is, because undirected is really just a collection of directed graphs. So it's just like an extra optimization on which particular directed realization you want to pick. Yeah. So solving a directed graph communication problem is always more general than the undirected version.
we are given an undirected graph and want to find the maximum flow, what should we do?
Actually, it turns out this is exactly that. This is in good shape. This formulation is in good shape. This formulation captures both directed and undirected. So you just have to solve this linear program. So there's another advantage of writing it this way, is that it doesn't take into account, doesn't get too bogged down between directed and undirected. The only issue is when I write down these edges for the paths, just make sure, for directed you have to be very careful that they have to be directed edges. For undirected you just write them down and they're undirected edges. So that's the only difference. The formulation, the notation, everything is the same. So if you want to calculate the max flow, you just solve this program. We'll keep this program here on this part, on the second part of the board.
If it is undirected and there is a path from S to G, consider an edge from A to B, okay? If the path is coming from B to A, but the other paths are coming from A to B, shouldn't that one be shown as a minus one in the summation?
No, it won't be minus at all. Because you just use up that edge, whichever way you use it. There's nothing being subtracted. The total flow on that edge is just being counted, whichever direction it goes in. So the only thing is that just this, between the directed and undirected graph, the only difference is just here. Whether you count the edge as directed or undirected. If it's a directed graph, you should think of this as directed edge. Otherwise, it's just an undirected edge. No matter which direction it's coming in.
So following this question, you can interpret that phenomenon as putting two edges with the same capacity on both of the directions. Then for each conservative flow in the directed by directed graph, you can find a flow in the undirected graph. Because
No, but what's the point? But what is the?
I mean, so then that problem doesn't happen.
No, there's no problem there. I just want to. I think he had a question. I don't think there's a problem with that, right? You were worried whether one direction is this and another direction is that. You just count the total flow, without worrying what the direction is in undirected. In directed, of course, you have to count them separately. They're directed edges, so the direction matters, and you count the capacity constraint separately. I just realized one thing. There are multiple boards here. I was only using 4 parts. There's actually 12. I just realized it. So that should save us some time. Okay, so is this clear? So that's what the flow is. And to be able to say anything, how good they are or whether they are okay or not, we need some mechanism to say some outer bound so we can compare things, some kind of a benchmark. The outer bound or upper bounds are so-called cuts. Let's use this. Okay, what are cuts? So we'll in these lectures we'll visit a couple of types of cuts, though there are more than them, more than the ones we'll visit. Cuts come in variety of stripes and flavors. Of particular interest are so-called edge cuts. So there are 2 kinds of cuts that we'll talk about in these lectures. One of them is called an edge cut. The other of them is called a vertex partition cut, or just vertex cuts. Some people just call them vertex cuts or vertex partition cuts. So there are edge cuts and there are vertex cuts. And there are other types of cuts, but we'll probably not have to really visit them. What are edge cuts? So edge cuts are just a subset of the set of edges. And a vertex cut is really just a subset of the set of vertices. Just that. What do they mean? What's the, so that's an edge cut. It's really just a set. Let's look at edge cuts first. An edge cut is just a subset of edges, and you can say the value of the edge cut is simply the sum of all the capacities of the edges that you removed. So you should think of this. So the reason it's called a cut is you should think of taking out those edges E tilde out of the entire set of edges. At this point, I can even say that let's just think of the edge set as being complete. So it's a complete graph. And if some edges were not there in the original graph, just think of the capacities as being 0. It just helps with notation as we go along. Okay, just keep that in mind. And in that case, E tilde is simply a subset of edges that you're removing from the graph. You think of them as removing it. And then the value of the cut is how much capacity you got out, you removed out. A cut is interesting if an edge cut is sort of interesting with respect to the communication problem, let's say the Unicast problem, if the edges that you removed separates all paths from S to T. So an edge cut separates S to T. Well, I hope it's clear what it is, but the point, I guess, is that mathematically what it means is that for any path between S to T, there is an edge in that path which is in this set E tilde. There exists an edge E tilde. So for every path in the set of paths from S to T, there exists an edge E in this path such that E belongs to. Then you say this edge cut or this subset E tilde cuts the S to T. So that's why it's called a cut. What's the point of doing this? Well, the important point is that, and of course you can take any edge cut which separates S to T. And so the important point is that the value of E tilde is always an upper bound on the max flow. Hopefully it's not too hard to visualize. The point, I guess, is that flows have to go from S to T, and they must have gone along these paths. And each of these paths, the flow you can go on a path is limited by the minimum capacitated link along the path, right? And that's the weakest link. And at least one of those links, maybe even the weakest or maybe one stronger one, is in this edge set. So just putting together all of that must have been an upper bound on the flow. So this is a fairly elementary observation, and that's the reason of looking at cuts. So these are edge cuts. Is this clear? Okay. Vertex cuts are just subsets of vertices, and the point, I guess, is that they're very special types of edge cuts. So if you look at a vertex, the reason I call it partition, or it's called partition, is called, let's look at the simplest type of vertex cut. It's a bipartition cut. So the set of vertices is divided into omega and omega complement. And this is, I guess, the set of vertices. That's the cut. Omega is the cut. It's a set of vertices. And it induces a natural edge cut. The natural edge cut is the set of all edges going from omega, the vertex partition cut, to the complement. If this is such a cut, such an edge cut is called a vertex bipartition cut. So vertex cuts are really edge cuts, but they're somewhat specialized edge cuts. All vertex cuts are edge cuts, and bipartition cuts are like this, but you can have multiple partition cuts. So you could have something like this, omega 1, omega 2, omega 3, and then you're looking at all the edges between them. Okay. So those are multiple partition cuts. All vertex cuts are edge cuts, but not necessarily vice versa. So edge cuts are more, you get a wider class. Which one are, so the edge cuts themselves were upper bounds on, flow. So as such, vertex cuts are also upper bounds on flow, because vertex cuts are also upper bounds on, cuts are just edge cuts. Right, this is an IT summer school, so we are interested in not just flow, potentially other schemes. So it's not enough to just look at upper bounds on flow. It would be good if the upper bound we have is an upper bound on any scheme. Then we have a sort of a true upper bound on every scheme. Flow is an achievable scheme, and now you have a comparison between these two will yield some meaningful measure of how good flow is. So it turns out the following is true. So we'll see this. This is an important aspect. Is that for Unicast, whether it's directed or undirected, directed or undirected, max flow equals min edge cut. So you don't really need to do vertex partition cuts. Edge cuts themselves achieve, and this is equal to the capacity. So edge cuts are fundamental. That means, so I'll use this phrase that certain cuts are fundamental. That means, what I mean to say by that is that they are true upper bounds on any scheme, not just on flow. They're always bounds on flow, upper bounds on flow, but if I say an edge cut is fundamental, by that I mean that it's an upper bound on the value of the cut is an upper bound on every scheme. If it's a unicast problem, then whether the graph is directed or undirected, edge cuts are just fundamental. And in fact, they are also, the min edge cut is the right answer, is the correct capacity. But for directed, but for multiple unicast, the answer is quite different depending on whether the graph is directed or undirected. If the graph is directed, then edge cuts are not necessarily upper bounds on every scheme. Not necessarily. So they're not necessarily true upper bounds. But if it's an undirected graph, so I'm talking about edge cuts. But for undirected graphs, turns out they are. When I say they, I mean edge cuts. Turns out vertex bipartition cuts, or vertex multiple partition in general, are always true upper bounds, whether the graph is directed or not. Vertex cuts are always true upper bounds. There's a question.
Yeah, can you define what you mean by minimum edge cut? Like if it removes a fewest number of edges, value?
No.
Capacity of the edges?
The value is the minimum. So you understood what a cut was, what an edge cut was. It's a subset of edges that separated S to T, and there is a value of that cut. The minimum edge cut refers to the minimum of all possible such cuts. Minimum as in the value.
So of all possible cuts, the one that gives you the minimum value.
Yes.
Okay.
Values are numbers. Edge cuts themselves are kind of sets. So when I talk of minimum, I mean the value of the edge cut. So it's a bit maybe too much to write, so people just say min cut, in fact. So you won't just completely shrink the whole thing. So strictly speaking, it's the minimum of the value of the edge cuts. This is somewhat of an important distinction that tells you whether to look for edge cuts or vertex cuts. Right? This is, I mean, you're all fairly experienced students of information theory. So when we talk of the cut set bound in information theory, typically, I mean, that's more general. It doesn't not necessarily on a graph or direct wireline networks or anything. It's more general, cut set bounds. And when you specialize them to the graphs we are looking at and the communication problems we are handling, then the cut set bound refers to the vertex bipartition cut. So vertex bipartition cuts are always upper bounds, follows directly from the cut set bound of information theory. I'll give out some handwritten notes so you can also look at them. Yes?
Did you say that not all vertex bipartition cuts are edge cuts?
No,
So not all edge cuts.
the other way around, yeah.
But if an edge cut separates S and T, then it has to be a vertex bipartition cut because what is reaching from S is separated from
Aha, that's a good point. That's a very good point. And for unicast, that's true. But for multiple unicast, that need not be true. Let's do one quick example, and this is a very famous example. Here's this is two source destination problems. And this is a directed graph. Let's say all the capacities of the edges are 1. Okay, so I mean, I didn't write it, but let's say the capacities are all 1. So it's a directed graph and 2 unicast. What's the minimum edge cut? Can someone quickly see this? This is a good example, actually. You want to separate? Okay, so I never defined what. So I guess I defined an edge cut for one source destination pair. There are several ways to extend it to multiple source destination pairs. The one of the ways is so-called, actually this is called a so-called multi-cut, is that the edge cut separates S1 to T1 and S2 from T2 separately. We'll be precise about this. So, and you can talk about edge cuts that separates S to T is what I had. But if you have 2 unicast, then the so-called multi-cut, which is a certain type of edge cut, it separates S1 from T1. It also separates S2 from T2. If you remove this middle edge here, just this one edge in the middle, that will ensure that you separate S1 from T1, simultaneously separating S2 from T2. So that's kind of the bottleneck edge. So the min edge cut, the min multi-edge cut, is just 1. The value is just 1 because you just removed one edge. But you probably, and flow is also just 1 because you're limited to that bottleneck link. The total flow is just 1. So indeed, flows are always upper bounded by cuts. But there are schemes that can do better than 1, isn't it? Do you know this? This is a so-called network coding. The point is that you send both S1 and S2 can communicate separately at unit rate as opposed to the sum of being unit. The way to think about it is that if you send some A and some B here, and then you send A XOR B, this guy gets B, this guy gets A XOR B, and you can decode B here and decode A here. This is not flow because the relay node here mixed what it got and sent it. And someone asked what I meant by mix, and this is an example of that. Flows would never do such a thing. So this is an example. This butterfly would be an example of a directed graph where in multiple unicast setting, 2 unicast in particular, where edge cuts are not fundamental. Edge cuts are useful things to keep in mind if you have flows, as your natural achievable strategy. But if you're looking at capacity, then they may not be the right thing to think about. On the other hand, vertex cuts are always fundamental upper bounds. And I'll give out some notes, you can look at them, but they're really just the so-called cut set bound of information theory. But for undirected graphs, and this is interesting, if the graph is undirected, then edge cuts are fundamental. And the way to see it is the min edge cut is really no better than a min bipartition cut, a vertex partition cut. So the min vertex cut, so in other words, for undirected graphs, even for undirected graphs, the vertex cuts could be a little bit more restricted than edge cuts, but when you do the min of them, that means the minimum value of the cuts, they're the same. And hence, for undirected graphs, edge cuts are not are really the same as vertex cuts. Yes?
What would be a vertex bipartition cut?
Good question. What would be a good vertex bipartition cut? Well, removing all three here would be decent. That would work, right? Removing all these three would work. That would be kind of that would separate the sources from the destinations. So would this, and this. That will also cut them out. So vertex bipartition cuts involve just sources on one side, destinations on the other, and relays you can put wherever you like. Yeah, so that's good. Let's do this one thing and we'll take a quick break. Why is it true for undirected graphs, the min edge cuts and min vertex cuts, why are they the same? They're clearly not the same for directed graphs. This example tells you right away. The min edge cut is just 1, whereas min vertex bipartition cut is probably just 3. Can't do better than that. So clearly not true for directed, but for undirected, they are the same. So let's do a quick check on that. Well, let's look at an undirected graph. If you think of an undirected graph and you look at an edge cut on it, well, if it's an undirected graph and you take out edges, they just look like a vertex multi-partition cut. Right? If you just, so every edge cut on an undirected graph are just vertex multi-partition cuts. You have to just visualize them a little bit. Think of taking out edges. You separated S from T. Well, because the edges don't have a direction, if you separate U from V, you also separated V from U. So basically the only way of getting an edge cut is by having just partitions. You might have more than one, more than two. If you had two, then that was already a bipartition cut. So then you're just done. So the only interesting thing is an edge cut which is really a vertex multi-partition cut. And then essentially I'm claiming that let's see, the upper, when I say they are, what I mean is that the vertex multi-partition cut is really no better than just a bipartition cut. So let's just quickly see this. So consider multi-partitions. I don't know, in this case 3 partitions. And I want to claim that the edge cut associated with this is really no better than some, I don't know which one, but some bipartition cut. Why is that? Let's check. So consider this is an edge cut. This is an edge cut. It's really a vertex multi-partition cut. Let's say vertex three partition cut. And I want to claim that the value that you get out of this is really potentially only worse than a specific bipartition cut. Which one? Well, I'll claim that the value of this edge cut is only worse than the smaller of the following three, the smallest of the following three bipartition cuts. This one, where you just think of them as together, or this one, think of these two as together, that's a bipartition, or this one, where these two are together. In particular, actually, we can see that the vertex multi-partition, the value of this three partition cut is only worse than the average of these three bipartition cuts. And hence, there must have been at least one of these bipartition cuts must have been smaller, or they're all the same, in which case you're also okay. Let's quickly see this. This is the kind of thing that comes in handy. And we'll need this calculation later on, actually. Okay. We do need this kind of a calculation later on, so maybe we'll do it at that point. At this point, I think I just want to summarize the whole thing by saying that it's okay to look at edge cuts if it's an undirected graph, because they are more or less the vertex bipartition cuts. In fact, the minimum value is the same as the minimum bipartition cut. If it's a directed graph, then you really have to look at vertex bipartition cuts. And edge cuts are only bounds on flows, not on the capacity. That's really the summary. And for Unicast, it doesn't really matter. Whether it's a directed graph or undirected, edge cuts are just bounds in general, and in fact, they are the capacity also. The minimum value is the capacity. I do want to finish that part of the calculation, the main theorem, which is that max flow equals min cut. So the main theorem, we'll do it for Unicast, is max flow equals min cut. I erased my flow linear program, so let's write it. I'll write it here and we'll leave it there. So let's write down the max flow program. I think I had it on an earlier board. P belongs to set of all paths such that these f of p's were non-negative, and so look at any edge, look at all the paths such that the edge E belongs to the path P. You sum up all the flows, that should be the capacity of the edge, and this should be true for all edge in E. So this was how the program looked like. So this was a linear program. It's very useful to look at the dual of this linear program. Right? You're used to, linear programming duality. So this was a max program. The dual is a so-called min program. I'll just call it dual of the flow. How does the min program look like? Well, there is a variable associated with each of the constraints. Right? That's how duals are written, right? For every constraint, you have a variable. And so here, the constraints are on edges. So for every edge, you have a constraint. So you have a variable in the dual with respect to every edge. Let's call those constraints D for distance. So for every E, you have a constraint called D of E. That's also non-negative. This was a non-negative program. So there's also non-negative constraints. Constraints are also non-negative in the dual. And what's the objective function?
summation of P.
Yeah, so this is the upper bound here. So this should show up for with respect to D. And what's the constraint on D? Well, that is with respect to when in your objective function, how many variables there are. And for each of those, you have a constraint. Well, in your objective function in the primal, you have a summation over all the paths. So you really have a constraint for each path. So for each path, you have a constraint. And what's the constraint? Well, the constraint is that
Summation of D over the path.
yeah. So if I sum over all the D of E, where E belongs to the path P, along the path, they have to be larger than the value, whatever is multiplying f of p. In this case, it's 1. You can also do it a little bit more relaxedly. This is a fairly standard kind of a duality. And the main theorem of linear programming is that the max, the dual and the, so there's a duality theorem that says that the max program is equal to the min program. The values are the same, and they're kind of useful in many ways. How do you interpret this? I mean, this we had a pretty good interpretation. We had an operational interpretation for this. The idea is that there are all these paths. Think of them as all paths. And flow is some information just flowing along these paths. How much is flowing on each path is denoted by this number f of p. And you just sum them all up. Of course, you can't put arbitrary numbers because on any edge you can't overdo things. Okay, so that's we understand the dual very well. Now so that's the primal or the max flow program. The dual is also has a meaning actually, and the way to think of it is there's really a cost on each edge. There's like a toll. Every edge asks the flow to pay a toll, and the toll is really d of e. The larger the toll, then the more critical that edge is or something. And what you're doing is you're just counting the total toll that's being charged relative to the capacity of that edge. If you think of all the edges as unit capacity just by putting more edges, then that's exactly that. So that's the right way to think about it. So that's sort of the total toll. Well, what prevents you from putting zero toll? That's the constraint. The constraint says that there should be a minimum amount of toll between an S to T, no matter which the path is. So look at any path from S to T and look at all the total toll collected on that path, which is just the sum of all the tolls along the edges of the path, and that should be at least 1. So the dual of the flow is with respect to these tolls, d of e, or distances, and you just sum up the total tolls. Why do we do this? Well, let me use this part of the board and we can keep this for the later second part of the lectures. I guess we had the value of the cut up there on the middle part of the board, the middle one up here. I wrote down the value of the cut. Let's just rewrite that in this language, and we'll see it's pretty much the same as this program. So if you look at the min cut, or just the min value of a cut, is, let's call this summation CE DE, or maybe I'm using the same D on sort of purpose. I'm abusing notation on purpose. Where, what is D of E? Well, I just had to, so here I'm summing over all the edges as opposed to just E tilde, except that D of E is 1 if the edge belongs to E tilde, 0 else. And the fact that the cut separates S to T means that along each path, you have the same, and because it's 1 or a 0, you have exactly the same condition. And then you can take the min if you would like over all such E tildes. Or equivalently all such D tildes or D's which are just 0 or 1. Look at that, and this is not a linear program by any means. It's a combinatorial program because the variables, what are the variables? The variables are this D of E's. And the variables are just binary valued, either 0 or 1. You don't really have a choice in this. It's a combinatorial program. So the min cut is a combinatorial program with values 1 and 0, whereas the dual of the flow is a linear program on this side of the board. They're kind of separated out, but can you take a look? They are more or less identical. In fact, the objective function is identical. The constraint is identical. The only thing is that the support or the set over which the variables can range is just different. The set here is the continuous set from 0 to anywhere, I guess, non-negative numbers. I guess there's no point, because the total length is 1, there's no point in having any individual one more than 1. So the total, I mean, any one particular edge, why would you ever want to put a total more than 1 if just the total total is 1? So here you have any number between 0 and 1. That's the dual of the flow. The cut is just either the extremes, either 0 or 1. So this is definitely a far more restricted set as opposed to the dual of the flow. And as you can imagine, that minimum program, the dual of the flow is definitely in general smaller than the cut, simply because it has a bigger range for its variables. For the same constraint, same objective function, it just can have more values. So it can only be smaller. And indeed, no surprise, flow is always smaller than the cut. So that shouldn't be a surprise. So it's kind of a sanity check. So if you ever want to show max flow equals min cut, what you really have to argue is that in the dual of the flow, when you try to solve the optimal D's, or among the class of optimal D's, there is one which is binary, 0 or 1, which is at the extremes. If you can do that, then you're done. And indeed, that is how one set of proofs go of the max flow min cut theorem. That's not how I would want to do it. That also doesn't quite generalize very well. What we would like to do is a more modern proof of why this program out here, let me call this, so this is called the dual of the flow. I think I'll start using the words dual of the flow. It's a linear program, and the min cut is a combinatorial program. They look very identical, except that one is a combinatorial program, the other is a linear program. And we'll see that the values are the same. And this method is somewhat modern. When I say somewhat, it's still about 20 years old. So let's take a short break. I think I didn't quite estimate how much time we need here. I'm also getting to know this audience. We definitely need a break though. Let's take a 10-minute break, and we'll be back by 10:30. We'll get started. All right, welcome back. I think I woefully, oh, sorry. Right, welcome back. I think I quite a bit underestimated how much time it takes to do this. The last time I gave it, I did it in 6 hours. So, and clearly, and I'm going slower than I did last time. So it's pretty bad shape here. But we do want to, these are not slides to speed up. So we can only, I just have to pick and choose. So what I'll do though is definitely to complete the main punchline, which is given that we set up the whole stage, we have the programs, we'll at least see that they're equal. We'll also try to generalize it for the multiple unicast. And then at that point, I think we have some options. I'll try to summarize various things. One of the things that the organizer said is that, and I feel as a lecturer, I should share my viewpoints on which are interesting problems, what are promising directions. I mean, given this is a whole open area, one of the goals of research and to do the work is to also get a feel for which directions to take. And so I'll try to share some of those things. One of my own experiences in this is that there's really a minefield, and there are several directions which are, you're really stepping into very deep waters. So it's good to know. So I think one thing that I'll try to share is where the mines are and what might be more tractable and so forth. So we'll try to summarize with those. I don't know if we'll cover everything that I had in mind, or at least I started off with. Okay. So there are several ways to show that, so the key here is, there's a program out there, the dual of the flow, it's a linear program. There's a program out here, it's a min-cut, it's a combinatorial program. They look pretty much identical, except that the variables are between 0 and 1, real numbers, and here they're just 0 or 1 extremes. How does one handle these two things? How does one show? So it's really, you can think of the dual of the flow as a relaxation of this program. It's an integer programming problem, and you kind of relax it. How does one show that they're equal? And the key idea is the idea of a random cut, is to not show. So what this is saying is that the optimal cut, or the min cut, is equal to the dual of the flow. That's too much work to actually identify which that cut is, which is how the traditional proofs went. That will be too much work, and that's not quite as illuminating. Instead, we'll show that even a random cut, appropriately chosen, will equal to the dual of the flow. So when a random cut itself is equal to the dual of the flow, there must have been a cut which equals the dual of the flow. Because in general, the min cut is only the min cut is only larger than that, and now you have a random cut, and which is equal to the value. So the minimum value must also have been equal to the value. So that's the logic we'll see. So instead of identifying the min cut to be equal to the dual of the flow, we'll show as appropriate random cut equal to the dual of the flow. And hence there must have been a cut that matches it. Okay, how do you find the random cut? What is the way to do the random cut? The key insight is the following, and the insight comes from understanding the dual of the flow from a slightly more geometric perspective. So let's look at it. I'm looking at it, and you can also look at it with me, and we'll identify some properties of the dual variables. The d of e's are like tolls or distances on edges. They're the weights on the edges that you're putting. That's the dual, how it looks like. The more important an edge is in the primal program, that means it's carrying a lot of flow, then probably you're putting also more d on it, more weight on it. That's the way to think about it. And there are some properties we can say right away that, so there are numbers on edges, and one thing you can say right away is that it should have a triangle property. At least without loss of generality, we can introduce a triangle property for these tolls. So that means if you have, what do we mean by triangle property? If you have three vertices, u, v, and w, let's say this is directed, I mean, this is true, it's directed or undirected, but let's say it's directed. So there are two paths to go from U to W, directly or via V. Let's say there are associated tolls. Let's call it D1, D2, D3. I guess there are names for them. D1 is really D of UV, D2 is D of VW, and D3 is D of UW. So there are tolls. I want to claim that without loss of generality, the tolls you put should satisfy the triangle condition that D of UW is only smaller than D of UV plus D of VW. If not, then you can choose smaller tolls. Choosing smaller tolls is only doing the right thing because it's a min program. So you really want to keep tolls as small as possible. At least that's what the optimal one is trying. So if you violate any such triangle property, I claim that can't be an optimal one at all. You can try to reduce it. Why is that? Well, suppose you violate a triangle property. That means the toll going from here to here is smaller than the toll going just directly. Well, then I can just reduce. So if you look at the end-to-end path, S is here and T is here, and somehow there is a path that goes via U and W. What happens between U to W is just local with respect to the global path. You knew that this path, where I went from U to W directly, had a toll of at least 1, because that was a constraint. Or you could have gone to U to W via V, and that also had a total toll of 1. Now, if this path was shorter, then there's no reason why this direct toll should be as large as D3. I could have reduced D3 to be equal to D1 plus D2 without violating the end-to-end toll constraints. Because by definition, this path here from S to U, U to V, V to W, and from continuous had a total toll of 1. So this path, I can sort of D3 could be reduced to D1 plus D2 without changing the constraints, and you only reduce the objective function. So it must be that you have the tolls satisfy the triangle relation. So that's one important property we'll see right away. So that's actually a very important property. What this means is that this gives us some kind of an ordering in terms of this triangle property gives us an ordering. So let's see what this ordering is. So on one end, so this is one observation we can make right away. This is an important observation, so ask me if you have any questions. There's one more observation, and then I think we are home. Look at, so I said, I think somewhere during the first part of the lecture, I said, I encourage you to think of the graph as being complete. All edges are there. It's just that if some edges weren't, then think of the capacities as being 0 on those edges. What should the toll be on the direct path from S to T? That's also an edge. It's just directly going from S to T. It's a very simple path, just directly going right away. What do you think the toll should be? 1, right? There's no point in putting toll more than 1. The minimum you should put is a 1, and there's really no point in putting more than 1. You might as well reduce it all the way down. So this toll is really just 1. All the other tolls are only less than or equal to 1. And the direct path toll is exactly 1. This gives us a geometric picture. So here's S on one side. Here's T on the other side. And let me draw kind of a line here. I want to think of this as this distance is 1. D of S to T is 1. And now I can order vertices based on how far away they are from the source. I don't know, Vn or something. And there may be some vertices continuing on. There's no reason why they should be more than 1. I guess they could be at T. They could be exactly 1. For some reason you chose that. So what did I do? This is really a geometric picture then. I ordered all the vertices of the graph based on how far away they are from the source S. So V1 is the closest to S in terms of the toll ds comma V1, or the distance S comma V1. That's why D for distance. It's really a distance. Right? This ordering comes up naturally based on the dual variables. One quick thing here, what's the distance between V2 and V3 on this line? This distance? This distance, is it dV2, V3? No, right? That's not how I did this points on the line. This starts at 0, this starts at 1. This ends at 1. This distance is not dV2, V3. This distance is really this distance, dsV3, minus dsV2. So this distance is really dsV3 minus dsV2. That's how I did the diagram. I put points based on the distance to S. How does it relate to dsV2, V3? I mean, that's a critical question, actually. You were right. How is it related? It's only, in general, less than or equal to dV2, V3. Okay, that was good. That's why I need the triangle property. In general, the inter-node distance only shrunk with respect to what the tolls were saying, what the dual variables were saying. Okay? All right, now we are really set to talk of the random cut. My random cut is an edge cut. Furthermore, it's actually just a vertex bipartition cut. It's simply randomly taking a theta between 0 and 1 and just cutting it like this. It's a random cut, random in the line over the line 0 to 1. So the randomness is just, you think of variable theta, uniformly chosen between 0 to 1, and just draw that theta line. And the cut is simply the vertex bipartition cut between all vertices here to all vertices on this side. By definition, it cuts S and T, because there are two extremes. And this is a vertex bipartition cut. It's a random cut. So let's calculate the value of the cut. Can you help me calculate the value of the random cut? Maybe you can think about it too. I want to calculate the expected value. Let's look at any edge, any pair of vertices. When are they cut? Well, V2 and V3 are cut only if the line happens to be between V2 and V3. How often are V2 and V3 cut? Well, it depends on the distance between them. In fact, that's exactly the frequency with which, or the probability with which V2 and V3 are cut, because it was just randomly, uniformly chosen between 0 and 1. So the value of the cut is simply sum over all edges E C of E, let me call it d tilde of E. What is d tilde? D tilde is this one. Let's call this as the new toll, d tilde. Its d tilde of E is defined to be, let's call this d tilde V2, V3. It's only some of the values are only smaller than what the dual variable said. So the value of the random cut is C of E d tilde of E, and d tilde of E are some numbers between 0 and 1. And those numbers were in general only smaller than those, could have been no larger for sure than the dual variables. The important thing is that the d tilde E are only smaller than the dual variables d of E. Strictly speaking, I mean, if you want me to be precise, then what you should do is all these properties are true with respect to the d's being the optimal one. So if you want to think of it, these are all d star, the optimal dual variables, and everything is with respect to the optimal one. So look at the dual of the flow, look at a optimal solution. So that gives you a set of d's, I call them d star. Use that. First you observe that the optimal one should satisfy the triangle property and this property. You use this observation to create this geometric picture in your mind. There's S and T and all these lines are in between. And they're all with respect to the optimal dual variables. And you take a random cut. The randomness is with respect to this geometric picture. And the value of this random cut, expected value, is equal to C of E d tilde of E, where the d tildes were only smaller in general than, or at least were no larger than the dual of the flow optimal values. And because this is a min program, so this value is in general no larger than the dual of the flow. So which means that a random cut itself is in general smaller than the dual of the flow. There's no way that could have been happened because the min cut itself was larger in general than the dual of the flow. So the only explanation is that min cut equals max flow. So this is a very elegant proof that doesn't get to the complexity or issue of showing that the min cut, which is sort of a combinatorial thing, matches the dual of the flow, which is a linear program, but it's an alternative proof using the power of randomness to show that that's really true. Is this clear? Are there any questions? This is an important, this is really one of the punchlines we should have done earlier in the first part of the lecture. The crux of this whole proof really lies on this one part of the board, which is this geometric picture. This is it. Once you realize the dual of the flow has this distance properties, then you can write down all these distances on just one line, and you're done. Once you put them all on a line between S and T, then the cut is natural. Identifying the exact cuts, the min cut, is still involved, and that's somewhat of a different topic. But to show that the min cut is equal to the max flow, you just need to pick a random cut. Even a random cut will work. So the key is to just have this line representation. I mean, this geometric picture is particularly simple. It's just a line. Okay, this is the Unicast story. And nowhere did we really use directed or undirected. Nowhere have we, this proof works just as well for directed or for undirected. Like I started out, like I said in the early part of this talk, the goal of these lectures really, or the challenge of network information theory is really multiple unicast, S1 to T1 and S2 to T2. The question is, what can be said about such situations? In other words, we did a fair amount of work, flows, cuts, edge cuts, bipartition cuts, and so forth. What is known about multiple unicast scenarios in these, for these settings? Let me summarize the main results, and then we'll see how this kind of a proof extends to one of the results that I'll summarize. I'll leave this board up here. Let me try to summarize, and this is sort of important messages from this. Now, we won't prove all the things that I'll summarize, but we will prove something that will make use of this fact that we have this line representation. So let's think about multiple unicast. So we are moving on away from unicast towards more involved ones, multiple unicast. And so far for unicast, whether it was directed or undirected didn't really matter. Whether it was edge cut or vertex bipartition cut didn't really matter. It didn't really matter whether you were careful or not, whether you were being picky or not. You just picked directed or undirected. You didn't really care. No, didn't hurt you. Didn't really care whether you took edge cuts or bipartition cuts. Didn't really matter. They were all the same. Everything worked out in pretty much any combination you chose. But that's not to say that's nowhere near the truth for multiple unicast. Very different. In fact, it's a whole a minefield. And particularly, there is a huge gap between the types of results one can show between directed graphs and undirected graphs. There's a huge gap. These two graphs are just tremendously different in terms of they are understanding complexity in every way. In particular, for directed graphs, we have understanding in both, but it's just that they're very different types of understanding. For directed graphs, all the results that exist are, you could say, depends on how you view it, but sort of negative. In general, max flow is nowhere near edge cuts. Whether you think of edge cuts as in the usual notion of edge cuts or vertex bipartition cuts. Max flow is, in general, very far away. Depends on the graph, but you can kind of create graphs that just make the gap really bad. And this is true for edge cuts and also from vertex bipartition cuts. Furthermore, these vertex bipartition cuts and edge, so it could also be that edge cuts are very far away from capacity, and it could also be that vertex bipartition cuts are also even further away from capacity. So it's like max flow is out here, arbitrarily far away is an edge cut, arbitrarily far away is the capacity, and even further away is vertex bipartition cuts. So this is kind of the ordering. Flow is here, it's an achievable scheme. And then you have an edge cut, which is unclear whether it's larger or smaller than capacity, right? For directed graphs, edge cuts are not necessarily upper bounds, true upper bounds. And then you have the capacity itself, which is somewhere in between that you don't know. I guess the point of looking at flows and cuts are because they are tractable. You can look at them, you can understand them. Flows in particular also constitute engineering schemes. So you can actually use them. Cuts are easy to write down, they're combinatorial. They're easy to write down, doesn't mean they're easy to actually evaluate because they're combinatorial. See, the random cut doesn't quite give you a method of actually calculating the value. It's like a proof technique, really. If you actually want to find the cut, you have to do some work. Turns out that even doing that work is very hard for multiple unicast directed graphs. That means even combinatorially, that's a hard problem. So it's in computational complexity sense. So it's a combinatorial problem, and people understand what might be better good algorithms, and it belongs to an NP-hard class of problems. So if it's a directed graph, things just look bad, whether you think of it from computational points of view or even just communication points of view. And in fact, well, if flow is not optimal, then maybe network coding is, or linear network coding is. And these are the sort of the if you follow this area of literature, basically there are only negative results that basically say that no amount of how creatively you define linearity, they will still not achieve capacity. So this basically says that you really don't have much structure for, or at least linearity is definitely not the right structure for capacity achieving codes. In general, when people say wireline networks and graphs, network information theory is open, what they really mean is the directed setting. And the results are all not very, I guess there are results, it's just that they're also saying there's probably not very much structure there. Undirected, on the other hand, things couldn't be more different. We've already seen, though actually I don't know if I ever got to prove it, that edge cuts are the same as vertex bipartition cuts. I already said that. I think I said that. I'll give you some notes so you can look at it as well. But I did make that claim that edge cuts are okay to look at in undirected because they are fundamental. So we already got a good start that edge cuts are okay to start off with. Turns out, and this is an important result, is that max flow is not too far from min edge cuts. And this is an important result that we'll try to see. So max flow, so several things are known, and some things are only conjectured. So let me first say some conjectures, and then I'll tell you what are known. So these are also interesting open problems, by the way. So a long-standing conjecture in undirected graphs, multiple unicast, is that flow is still optimal. So this is a conjecture, though. Another way of saying it is that network coding doesn't help in undirected graphs. No amount of network coding helps in undirected graphs. This is a conjecture, and I mean, we know, of course, it's true for Unicast. We've already seen this. Turns out it's also true for Unicast, to Unicast. So we've seen it for Unicast, and it's also true for proved for the geometric picture that we have will readily allow us to derive this, and we'll do it right after we summarize these results. So it's been proved for 2 Unicast. But for 3 Unicast and more, it's a long-standing conjecture. It's kind of a very strong conjecture, actually. It's something to think about. But what is known, though, is that it's not too bad. It can't be really far away from capacity. And what is known, so that's known. I mean, it's conjectured to be exactly tight, but exactly capacity. But what is known is that that's not too far away. In particular, max flow, of course, is less than capacity, is less than min cut I mean, this is just true because min cut is always an upper bound on capacity. So these are just known facts. I mean, all these inequalities I wrote are just clear. Max flow is an achievable scheme. It's less than capacity, and edge cuts are upper bounds on capacity. So these are just known things. But what is known is that max flow is not too bad. Where K is the number of source destination pairs. Not the size of the graph, but the number of source destination pairs. And this result is just true for any graph. So this is kind of a universal result. So you potentially get some weaker results in this constant simply because it was a universal constant. Doesn't depend on the exact graph. But the message to take away from it is sort of more qualitative, which says that that flow is not too far away from the cut. In fact, like I said, it's conjectured to be the optimal. It's just that you can't get to it from doing cuts. So if you want, and it's also not possible to improve it. In other words, there exist graphs where this lower bound is more or less tight. So if you want to show this conjecture, if you want to work on this conjecture, then improving this inequality is not. No, what I mean to say is that these inequalities are kind of obvious, almost tautologies. So this one is sort of the harder work, and we'll use this geometric interpretation to prove it. We'll do it right now. But this one cannot be improved much either. It's sophisticated results, but the main point, I guess, to get to the punchline is that this cannot be improved. There exist graphs where the gap is that much. So if you want to show this conjecture, you shouldn't be looking at cuts. You should be looking at some other upper bounds, which are not coming from cuts. So if you follow network information theory, there's something called the LP bound, the linear programming bound, and so maybe that may be a direction. But that's not nicely either. Definitely not a linear program. I mean, I guess it can be a big, huge linear program, but it doesn't definitely look like the dual of the flow or anything. See, the good thing, I mean, why is cut so fascinating? Someone was asking me here. Well, one of the reasons is simple, but the other thing is that it also is really the right thing. It's mathematically, it's exactly the dual of the flow. It's just ready-made. It's really right there. So cut is somehow it has that aspect to it. Other information theoretic upper bounds, we have some idea, right? You probably have some ideas too, working on the various multi-terminal problems, but there's no generic structure like the cut or general upper bound that you can just ready right away and evaluate something. Each multi-terminal problem, the upper bounds are somewhat delicate. They're handcrafted for that purpose. So a good problem to work on would be along the way to understand how to drive more systematic upper bounds. This is a story for undirected. For directed, things are kind of tough. Actually, every question is tough. Are flows good? Well, no, they can be really far away from everything you can think of. Capacities, from edge cuts, from vertex bipartition cuts, all the quantities of interest. They're kind of far away. Are cuts easy to calculate? Well, no. In directed graphs, cuts themselves are very hard problems. They're NP hard. And in fact, it's also known that they're even hard to approximate. So that's even sort of even worse negative results. Not only are they hard to calculate exactly, they're even hard to approximate them in any reasonable way. So no efficient polynomial time or efficient approximation algorithm does well. And well, if flows are not good, then maybe network coding is, and even that is sort of negative. No amount of sort of structure, particularly linearity types of structure, work. So directed graphs are quite a tough scenario. Of course, you might ask, now there's a sort of two different directions to take. Why do we work, which one should we work one or over the other? Which one do you prefer? In graphs, people work on directed and undirected for independent interest. But much of this motivation, much of the motivation I started out this is to sort of do communication. And in much of the networks we are used to, are they directed or undirected? Directed? What about wireless? Are you on wireline? Well, it's a choice, isn't it? If you're engineering the network, you really have a choice in how you want to engineer the network. I mean, you can choose to only put a transmitter and receiver on one end, but many of these wires can be multiplexed. In fact, they are all the time. And wireless definitely so. Radios can transmit and listen, maybe half duplex mode, but they can transmit or listen, and they can choose. And one of the messages of this direction is that you really, undirected is a direction to go towards, is something you want to engineer towards. It also affords schemes that you can build at that point using the undirected nature that you sort of engineer. Directed is just intrinsically harder. But one can ask a little bit more, so that's at the engineering point of view. One can also ask more mathematically, what is it about undirected that really makes it seem to work? Whereas directed is so different. I mean, where is this phase transition, or why is this such a stark difference? It's not clear, it's unclear, but one can slightly loosen or get undirected-like results of this type, where flows are maybe nearly optimal, not far away from the cut, these kind of results, even for directed graphs, as long as they have some more structure in them. Okay, as long as they have a little bit more structure in them, then one can say undirected-like results. It's just that worst case directed graphs are hard, or sort of arbitrary directed graphs are hard. What structure about undirected are we really getting? Well, undirected is somewhat a little too special. It's for every edge from U to V, you also have an edge from V to U, and the only thing that's constraining them is just the sum of them. Sum of the capacities is the same. And you have the flexibility to pick whichever way you want. That's kind of what undirected is. And that's true for every pair of edges, by the way. Turns out that one can get undirected-like results, even with a general directed graph, as long as you have this undirected, quote-unquote, flavor end-to-end between the source and destination. That means for every path from S to T, it's a directed graph, so it's a directed path, there is a similar thickness path from T to S. So in other words, if you have end-to-end cycles from S via T to back to itself of the similar width from S to T and T to S. This is, you can say, broadly undirected like flavor. You have the cycles, but it's network-wide cycles relating S to T and S1 to T1 and T1 to back to S1. And you have similar cycles from S to T2, T2 to S2. Such network-wide undirectedness, it's quote unquote, it's not really undirected at all by any means. It's just network-wide cycles relating ST. Again, you have undirected like results. That means max flow may not be equal to, well, I don't know the conjecture there because it may not be exactly capacity, but it is known that they're not very far away from min cut. But you have to be careful because for undirected, I can safely write min cut without being specific about whether it was an edge cut or a vertex by partition cut, because the minimum of both were the same. But for directed graphs, that's not clear. In fact, we know that it's not such a thing. So anytime you have this network-wide undirectedness, like what I said, turns out that edge cuts are fundamental, even for such directed graphs. So again, good things sort of tend to happen. The min edge cut is not the same as min vertex by partition. They could actually be far away, but this time edge cuts are fundamental. So in fact, it is a sharper statement than just vertex by partition cut. And furthermore, the flow is not far from such edge cuts. So really, undirected sort of helps you also mathematically to get a feel for what aspect of directedness is making it hard, or what aspect of undirected we really need. It's relatively loose. You just need this is picking at it from a more abstract point of view. More engineering point of view, I think one can probably even direct locally just there. Broadly, what this is saying is that feedback, what do I mean by S to T and back from T to S, is some kind of feedback schemes. And traditionally, feedback is used at a physical layer just to improve reliability, or even maybe, right, that kind of thing, or make complexity or reduce the complexity of communication. Here, what this is suggesting is that in networks, having this feedback path is not so much feedback as much as affording you multiple paths from S to T. Just that reverse path helps you loosen the complexity of the problem in terms of the directedness of the graph. And that flexibility is enough to just, at that point, let you work pretty much with flows. So if you're thinking of it from an engineering perspective, then you want to engineer towards that kind of a structure, graphical structure, where at that point flows work out quite well. Okay, this was a bit too much to write down here. That would take too long. But are there questions on this kind of a summary? This is an important summary. In the remaining 45 minutes, we'll try to prove this one. It's a very, given that we did the hard work on showing that geometric figure, I think it's definitely worth seeing the multiple unicast version of it. And surely for 2 unicast, where it is actually equal. Again, a certain random cut is equal. So that will do the rest of this talk. But I just wanted to summarize and say the punchlines before we get there. The flavor is different. One of them is more high level, and I'm trying to give directions. And that one will get down into more detailed math. So I wanted to separate them. There's a question.
How is it different from the Unicast? What is the capacity of the whole graph?
It's not known. And the whole point of all of this exercise is towards getting to it. Capacity is defined information theoretically as there exists a scheme which does set the rates and is the largest possible thing. Capacity is just operationally defined. And the whole game, why are we talking of flow or cuts, is to get towards it. Capacity is kind of, if you think about it in this type of an inequality, it's sandwiched between min cut on both sides. And min cut is something that you can experimentally calculate, evaluate for a given problem, and hence you have a handle over it. Any question on this? Yes.
Can we talk about a graph when it's kind of hybrid? There is directed and undirected edges.
Yeah, I guess.
And it is as hard as directed.
You can imagine, right? If you don't put any more structure on where the undirected is, then there would be. I told you one kinds of directed which have enough structure, which are network-wide cycles, relating S to T and T back to S. Those things are what I said can be attractable. And also I think that kind of structure is really required. One can show certain things about them. Any question, Vinod?
In the case of directed network, what's the relation between the network coding and the capacity, not by express? I mean, you're saying...
Well, I mean, in principle, I don't know what you mean by network coding, but if network coding refers to any scheme, then the optimal network coding kind of by definition will get to capacity.
No, you said maximum is arbitrarily far away from express in the directed network.
Correct.
And you also mentioned that it's also arbitrarily far away from the capacity.
It could be, yeah. Could be, yeah.
What about agent? Oh, we do not.
That's the problem, yeah. Yeah, network coding, if you don't put any constraints like linearity or something, will get to capacity by definition.
You also mentioned that even some certain amount of linearity also one cannot get to express.
Yeah, so those are results by Ziegler et al. Yeah.
Okay, so by certain amount of linearity also you cannot get to capacity also.
Yeah, you can't get to capacity either. That's right. Actually, in those examples, you can get to edge cut. You can't even get to edge cut, and edge cut was the capacity in those examples. Yeah, in that example it was. So it kind of solved both things in one shot. Yes?
Is there like a way to rewrite an undirected problem the directed way? Is there any special cases?
If you think about it, the proof of the unicast, what the question was, good, thank you. The question is that, is there a way to write undirected as some kind of a special type of directed, and then we can see a little bit better. But if you looked at the whole proof, I mean, everything is up there for the unicast. We didn't really need any notation change between directed and undirected. And we'll see in the rest of this second part, before we end, for multiple unicast, again the notation pretty much doesn't change except one small critical stage at the end. It's not so small, turns out. But that's it, actually. So they hinge on something fairly delicate, or delicate looking at least. And the notation is powerful enough to capture directed, undirected until a certain stage. We'll see that, actually. It's not a matter of notation change, I think. It's, yeah, we'll see what that is. Any other question? I guess we're taking all the questions before the end because rest of the remaining parts of this lecture are somewhat more, yeah, they're mathematical. So we'll just do that. Any other questions? Yes?
It's a question slightly in the earlier part. What is the value of the multi-partition cut?
For undirected graphs, they don't make any difference. For undirected graphs, the min vertex bipartition cut, the min edge cut. For an undirected graph, an edge cut is just a multi-partition cut. Because once you remove edges, automatically they're undirected edges, you just get partitions. So multi-partition cut is just an edge cut in general. A general edge cut looks like a partition cut for undirected graphs. For directed graphs, they're just more different. Yes?
So those definitions depend on the type of the, unicast, multi-unicast, right?
Sure.
So what you just said? I mean,
it's true for pretty much any kind of definition of cut you think of. So I don't know the question. You mean?
So the question is like for multiple unicast, can you say like the vertex multi-partition cuts for undirected graph is equal to?
Yeah, yeah, they are. We didn't prove them here, but they are. And that fact is true whether it's unicast or multiple unicast. So edge cuts in general are just the same as vertex bipartition cuts for undirected graphs. Just that. Any questions? Okay, let's do something very specific, and we'll focus on undirected graphs. Actually, we'll see that the notation is similar, same as for directed graphs, and at only one stage of the proof, in fact, one corner of the proof, it will only work for undirected and it won't work for directed. That's pretty much how it will go. And what will we show? We'll show that flow is not far from the cut. And because these are undirected graphs, we won't worry about what the type of the cut is. It's just an edge cut. The only thing is that we'll work with multiple unicast. So I have to be more careful. What does it mean to say flow and what does it mean to say cut? Because now let's say 2 unicasts. There are 2 source destination pairs at communicating rates R1 and R2 respectively. What do I mean? So it's not really one number. It's a pair of numbers. So when I talk of flow, maybe there's flow 1, flow 2. It's really a tuple. And similarly, when I look for upper bounds, like cuts, I really want, I guess, a pair that kind of dominates this pair. So you have to be a bit careful because it's really a region, I guess. In general, for K unicast, that means K source destination pairs, it's really K dimensional region. And you want, I know when I say flow, it really means it's a K dimensional flow region. And when I talk of cut, I probably want to talk of a K dimensional cut region. And say, when I say they're close by, I want to say they're close by as this region to that region. Okay? So you have to be more, somewhat more careful. One way to deal with this, let's see. Actually, I really want to reuse much of these, much of the notation and proofs. In fact, they're nearly identical. So I'll keep them and I'll rewrite what we need here. So that way you can look at them and also see what I'm writing. So one way to handle this tuple, I guess you're used to many of you must have seen multi-terminal information theory. So if you look at two-dimensional region, instead of that we look at some one-dimensional values but just parameterized. One way to do it is to look at, I guess, some capacity, right? That gives you a certain aspect about the region. You can look at symmetric capacity, that gives you another aspect. Or more generally, symmetric capacity kind of gives you the maximum value where R1 equals to R2. More generally, one can look at, so if you have two-dimensional region like this, R1, R2, and you have some region, it's convex, because you can time share, so its capacity regions are convex. So one can ask, I can take a direction like this, D1, D2. D1, D2 refer to demands. So you can think of them as some kind of direction. And I ask for this point, let's call it lambda. So this point is lambda D1, lambda D2. And lambda is kind of the largest value along that line. If D1 equals D2, then lambda will be, and equal to 1, then lambda will be the symmetric rate. Okay? So so that would be a kind of a parameterized. So I guess the rate region is now parameterized by D1, D2. And you fix that, and now you say, and if flow is not far away from the cut with respect to that D1, D2, then you probably have a good say going. And if you can say that for every D1, D2, then you probably got the whole region. Okay, that's the kind of notation we'll use. So that will help us reuse much of the notation. So what is the maximum flow that meets this demands D1, D2? What's the largest lambda? So such a flow is called not just called max flow, it's called a max concurrent flow. Just because it's concurrent in the sense that there are two sessions going on. That's the concurrence aspect. Well, it's maximum overall, maximum lambda. You want to maximize that lambda as large as possible along that line, such that, well, again, you have all these flow constraints. So if you look at all the flows over all the paths from Si to Ti, and look at the flows on them, then this should be larger than lambda Di. Is that right? Because you want to make sure, so lambda is achievable if lambda times the demand is achievable along with all the flows put together. Previously, in Unicast, we had only one D. So without loss of generality, we just called the demand as 1. In which case, lambda was actually equal to this, and we just moved it up to the objective function. So you should be able to go back and see this is the primal program. And you have the usual constraints. That means for every edge in E, as long as look at a path such that the edge is in the path, then f of p should be less than the capacity of that edge. That's just the same thing. And all f of p is non-negative. So if you look at this and the top board, number 3, then it's more or less the same, except that there lambda was actually equal to summation f of p, so I could just move it up there. Here it's not so clear because there are two different two or k different sessions, and so this is true for all I 1 through k for all sessions. Okay, so it's a bit more involved. Okay, what's the dual of the flow? By now we have some idea. Again, there is one variable for each path. So those will be the constraints. So you'll have a constraint for each path. And you have paths between Si to Ti for each I. So you have a lot of paths. So those are the variables of the dual program. And what are the constraints? Those are the constraints in the dual with respect to these paths. The variables will be with respect to, so now it's a little more involved because there are two kinds of constraints. One was the edge capacity constraint, and that was there even before. That we had before. So you always have tolls on the edges, or the distances on the edges. That you have as before. But you have a new thing, which basically says that the end-to-end flow on any, for any given session I, the end-to-end total flow must be at least lambda di. So now I guess you have new parameters Li. So let's write down the dual. It's a min program. So we can tend to write it essentially like this. Such that, well, you have the usual constraints. That is, for every path belong to P SITI, summation DE is larger than, turns out, Li. And actually, I should get my notation right because I'm going to share my notes with you. Okay, so might as well use, I think I was doing fine. What are these LIs? These LIs are the variables associated with this constraint. And they basically say that, and this is summing over all E such that E belongs to the path P, and this is summing over all the sessions K. I mean, it's too much to do the dual here in your head in these few minutes, but I'm hoping you can at least look at and recover the Unicast. I'm hoping at least you should be guided by that. And what did we do when we did the dual of the flow? Well, one of the first things we did was to sort of simplify it. And the way we simplified it, I guess, is by writing down, making some observations. That's what we did in the middle part of this boards, right? We made some observations. In particular, we observed the triangle property. Well, let's make some similar observations here, and then we'll write the geometric picture. First thing we can say is that, I need to understand what these D's and L's are. So there are two things here, D and L. D for distance, L for length. So they're kind of similar units, but they're capturing slightly different things. The D's are distances of the edges, so we're going to use them critically to put points along the line, or if there is such a thing as a line, whatever the equivalent will be. What are these L's? Where these L's, you should interpret them as the end-to-end length between Si and Ti. There's one for each session I, and it's like the end-to-end length. So previously I wrote down that d star of S comma t was 1. the end-to-end length was 1, and no point in having the direct path having length any more than 1. So here you should think of them as Li. So in particular, you should think of Li really as d star, or I guess Li star, at the optimal, when you try to solve them all, dual of the program, the direct path from Si to Ti, the distance will be this minimum distance length Li. So L is like the minimum distance path. So that's the way to interpret that. At the optimal value, this inequality should also be an equality. There's no point in having some slack either. So that should also be true. If you put these two things together, if you make these observations, then, and of course there should be a triangle property too. The D should have a triangle property. Why? Because of this kind of a length thing. If you have, it's the same argument as before. Previously I just wanted the end-to-end length to be 1. Now instead of that I have different lengths for different sessions. If all these sessions are the same, so each session could just be different. So you have different lengths for different sessions. So triangle property is still the logic is still exactly the same. So D's should also satisfy the triangle property. The D star, the interesting D's will satisfy the triangle property. So with these things, I can write down the dual slightly differently. Let me just normalize. So this is E belongs to E. Because I know that in the optimal value this was going to be an Li, and I know that Li star in the optimal value was equal to 1, so I might as well write the dual program just kind of normalized this way. Min, what does it min over? So the whole point, I guess, was that I want to get rid of this L. See, this never existed in the Unicast. And that was good because when I looked at the cut had only the D's because there was just values on the edges. Now you have these lengths, and it's kind of a end-to-end minimum distance paths. It's a bit of an annoyance. The key is to just identify the minimum distance paths as actually the direct path from Si to Ti. And that's all I did. We just normalized it. And you minimize over all D, which are non-negative, and satisfy the triangle property. That's the dual of the flow. It's more or less the Unicast case, except we've sort of normalized by these demands. There I knew that D of ST was exactly 1, whereas here I can't quite say that because I just have to normalize by, I have to kind of weight them by different sessions have different demands. Okay, so that's the dual of the flow. What about the cut? How does the cut look like? The flow was complicated because you had to worry about these demands. The cuts are also complicated. Correspondingly complicated. Previously, a cut was just any cut that separated S and T. That means you removed those edges and bingo, no path connected S to T anymore. Now there's S1 to T1, S2 to T2, and so forth. How do you quite handle that? So in general, what you do is you take a cut and you take a look at which SI-TI pair it separated. It might happen that a cut doesn't separate all SI from their corresponding TIs. Maybe you have to consider different types of cuts to get the right upper bound. So you might want to look at, so what I mean is the following. So look at the cut as the following. So I'm going to look at, I guess I said that edge cuts are fundamental, but anyway, vertex bipartition cuts are definitely fundamental. They are the cut set bounds. So let's look at an omega. It's a vertex bipartition. and I say d omega of E is 1 if, I guess let's call it d omega of E, let's call it E as u comma v, then if u belongs to omega, v belongs to omega complement, it's also 1 if u belongs to omega complement, v belongs to omega, I mean depends on directed or undirected. If it's undirected, then you allow for both directions because there's no real direction. But if it is directed, then you only have one direction. We're doing the undirected case, so let's focus on that. So I mean that's why I wrote it down. If it's directed, then you'll only have one way. Okay. So that this is a special type of. I'm using the same D on purpose because that way I can ask you to compare to the dual of the flow. Let's see. So I don't want to erase that line. That was a useful figure to have. But these observations, I think we've said them again. So we'll keep this line. This is useful. What do I have? I have the dual of the flow out there, and I'm trying to write down the cut. Okay, so that's what we're doing. I guess the dual of the flow is out here as well. I'm trying to write down a corresponding cut that we can see is more or less the same, and hopefully at that point we can see some geometric picture and we take a random cut. So that's really the goal. Okay, so that's what we are going for. The question is, how do you take the random cut? In the Unicast case, we had this line to guide us. We could use the dual of the flow, the corresponding D's that allowed them to write them all down, and then once we had them on a line, we can take a random cut. So the question is, what do you do for multiple unicast? How do you take the random cut? What is the right geometric picture? For that, we need to write down the cut. So at least it looks in some similar way. We're almost there. I said that's how a cut looks like. Omega is a vertex bipartition. Omega complement is a partition, bipartition. And d omega is just the edges. You put a 1 if it's across the partition. Otherwise, you put a 0. What's the value of the cut? Well, what you do is you look at all the edges crossing the partition. That's the value of the cut, right? That's definitely the value of the cut. That's the total value. But how good was this cut in terms of separating SI to TI? Well, this in general is, so how good was this in terms of separating? Well, then what you should do is, this is an upper bound in general on all the source destination pairs that were separated. So if I look at the d omega SI TI, if SI and TI were separated, then that should be like a 1. So all the rates, you look at the rates of those sessions which were separated by the cut omega. So this is the cut set upper bound. I just wrote it in the language of d omega. I do know that the rates are no more than lambda di. So RIs are, what are the rates? Just lambda di. Right? So this is lambda di. So I get lambda is less than or equal to, by the way, this is called sparsity, or the sparsest cut, defined as min over all partitions C of E, D of E, but normalized by D, I guess, omega SITI. How did I get this? All I did was to just write this as lambda di and bring this to the denominator. Okay. This equation is just reordering of this by writing the rates as lambda di. That's what we did, right? each rate, you look at the direction d1, d2, and r1 was lambda d1, r2 was lambda d2. And lambda was kind of as far as you can get on that line. So this S is also called the sparsity of the graph or the sparsest cut of the graph. It's also called the sparsity. So it's like the min cut, except it's a little bit more sophisticated because it's more than one unicast. It's 2 unicast or more. So you have all these demands D sitting here. Okay, let me erase this line. It's okay, we'll do this again. Okay, so this is the sparsest cut. Well, they're kind of far apart. Dual of the flow is out there, the middle left board, and the sparsest cut is out here. The sparsest cut is over all possible d omegas. The only thing about, so they look kind of similar, right? They look very similar. The objective functions are the same. The only thing is that the constraints, so the d's also satisfy the triangle property, so that's good. The only thing differing here in the dual of the flow is that in the dual of the flow, the distances could be any number between 0 and 1. And whereas here, they are restricted to be either 0 or 1. So it's the same kind of situation. This dual of the flow is a linear program. This is a combinatorial program, but the program otherwise looks the same. So it's again a matter of checking if the rounding or the relaxation is not too bad. But for Unicast, we had a clever way of doing it. And there was no loss at all in doing the relaxation or doing the rounding from integer to not. How do we know? What about the rounding here? It will be nice if there is any analog of that line representation and a random cut thinking. And indeed there is. And it's pretty much that of the same as that of the line. Is this clear so far? Because if it's not, then the rest of the things are only going to get more involved. If there's a question here, I want to take it. Yes?
Is the sparsest bipartition cost equal to a sparsest multicut?
Yeah. A multicut is used in a different language in this business, but multi-partition cut is probably what you mean.
No, I mean, the sparsest edge cut. Is the sparsest edge cut equal to a sparsest multicut?
Yeah. I think, yeah, this is not really meant for Blackboard talk. I think we have answered this question before, is that he's saying you're taking bipartition cuts, d omega, which depends on like omega, which is a partition, vertex bipartition. Why not look at general edge cuts? This is coming back again. We've discussed before, I think I said it several times in this talk, that for undirected graphs, unicast or multiple unicast, edge cuts and vertex bipartition cuts, the minimum values are the same.
My question was for the case of sparsest.
I meant it with respect to sparsest cut. In multiple unicast, I don't even know what a cut means unless I say sparsest value. Mm-hmm. Right? I have to be more precise. In a multiple unicast case, the min cut itself is not that well defined because there are many sessions.
You can compare min multicut or min edge cut to sum Q, right?
That's also true. It's also true with sparsest. Okay. So they're both true. Both are true. Any other question? Yeah, that was a little unrelated to this, but this is the sparsest setting. Okay, the rest of the things is a little bit more involved, and the key is to try to get a geometric picture. Okay, so I hope you can try to also think about it while we do the details of the proof. In the unicast case, there's really just one line. You can have S here, T here, and you just line up the vertices in the middle. And how far away they are from the source gives you a natural ordering. But now there is S1 to T1, and there is S2 to T2. How are you going to order them? I guess you can have one line which orders S1 to T1. All the vertices are ordered there. You can have another line where S2 and T2 are two ends, and the vertices are ordered. But they may not be consistent. So in other words, you can't just kind of put the two lines together and hope that they're consistent. Because the way in which the vertices might come from the source might be very different from in the two sessions. They can be entirely different. The two sessions are quite unrelated. So it's not quite immediately clear what the right geometric picture should be. But essentially what the cut is saying is that you should try to put them on lines. And where the dual of the flow may not afford you that. The variables that come, the D star that come out of the dual of the flow, out here or here, anywhere, I mean along the second board we have the dual of the flow. The D stars may not give you a natural line representation. So you have to somehow get there. So we'll do it in two different steps. In the first step, so in step 1, well, I guess there are 4 steps, but really 2 broad steps, and we'll sort of split them into 2 further parts. In step 1, we'll see that the min cut or the sparsest cut is really related to having lines. Is having as a line type representation. If you can get to a line type representation, then that's what the min cuts will try to get to. So that's what we'll argue with step 1. Step 1 will get from sparsest cut or the min cuts. By the way, sparsest cut, you should just think of it as language for min cut. It's just a more, like maybe a formal way of saying min cut, just to be precise. So sparsest cut is just the min cut. You want to get from sparsest cut to these line type line. I mean, this is just like an intuitive statement. Line type cuts. We'll see what they are. It was very clear what they were in the Unicast case. You just have to put the points on a line and just take a cut for the line. It's a random cut on the line. So we want to do that somehow for multiple Unicast. We can do that. That's step 1. In step 2, we'll relate line type cuts to the dual of the flow. If you can relate them exactly, that means the distances that come from the dual of the flow can be written as line type cuts, then you're just home, dry. Flow equals cut at that point. But many times you may not be able to, and then there will be a gap. And you want to argue that the gap is not much. So in step 2, we'll look at D star, the dual of the flow, which is basically anything as long as they obey the triangle property. So it's really like a general metric. So D star, dual of the flow, I guess it's just like a metric because it satisfies this triangle property. It's more or less a metric. And how close it gets to line type cuts. So this, if you can, and if the connection is, if it gets exactly close, that means they're the same, then you're just max flow equals min cut. This is what happened in the Unicast case. In the multiple Unicast case, in step 2, there will be a gap in general. But for 2 Unicast, k equal to 2, they match. And that's a useful thing to see. Okay, let's just complete that step. So I'll move this one up and this one down. Oops, not this one. Okay, let's look at step 1. What are these line type cuts? What do they even mean? For one thing, we can say that so the d omega we had was of the type that you either take they were either related to just 0 or 1. They were just extreme points. We can also try to relax it a little bit and still be a valid, still be the same value as the cut. One way to realize this is that it doesn't have to be 0 or 1. It can be 0 or 4 because it's normalized by the d omega SI. So 1 is not so critical. So it's just 0 or 1 or 0 or any other number is okay because of the normalization. So that's one thing to quickly see. So scaling up doesn't matter in terms of 0 or anything else. That's fine. So that's one type of thing. And another type of thing is that you can consider two different types of cuts and take their average. So take omega 1, that was a cut, and look at the d omega that comes of it, and take d omega 2, another cut, and take d omega 2 with respect to that, and you take the average of them, or any linear combination of them. So that's like a convex or a conic combination, I guess. It's called a conic combination. Then that's still, the min value is still the same. The conic value is still the same is simply because you can just scale them up. That is very clear. Why is a convex combination the minimum value not increasing? Well, you can't, not decreasing. Well, that's because, so let's look at two different, so let's say D of E is some alpha L, I don't know, L different convex combinations, where alpha L's are the values. They're not convex, they're conic combinations. Any positive value, alpha L, times, I guess, d omega L of E. Right? So different cuts, and I just average them. I want to argue that even considering such I guess these are not cut metrics. I guess these are not cuts anymore. This d of E is not a cut anymore. D omega was a cut, either 0 or 1. But these are more general things. But I want to claim that you can put that in the minimum value there, and that doesn't change the minimum value. It's increasing the space for sure, but it doesn't change the minimum value. How do you see that? Well, one way to see it is that basically the numerator and denominator, so suppose this is true, then look at the numerator of the cut, then summation CE DE is simply sum over all these combinations, convex combinations of I guess CE d omega LE. So that's just linear. So you can just write them whichever way you like. And similarly the denominator. This is summed over I. Because both numerator and denominator are kind of have this linear structure, doing an averaging will still get you the averaging structure. And now this is just a very basic inequality. So if you just take the average of two summations of numbers, then they're at least as large as the individual ratios of any one of the set. And any one of them individual is exactly a cut set. The cut metric is one of the cuts. So the left-hand side was really a conic combination of the cuts. The right-hand side was a specific cut. So having a conic combination doesn't really hurt. Okay, so this was an observation that so you can go from cuts to conic combinations of cuts, and that doesn't change the value of the cut. What's the point of going to the conic combination of the cuts? So the point, I guess, is that the conic combinations of the cuts has a nice geometric meaning. A cut alone has a meaning. One cut refers to just one line, and taking a vertex bipartition on that line. You have you can put points anywhere along a line, whichever way you like, S1, V1, S2, V2, whichever way. Put all the vertices on one line and just cut them in the middle. That gives you a partition. That's the representation of a cut. A conic combination refers to just multiple such lines. You can have as many as you want. And so really what this basically says is that the conic combination of the cuts basically says that the distances or the D's that you can get, I guess I'm using the word distances because they obey the triangle property. So it's like a metric. But this metric is not arbitrary. That metric should be in such a way that you can write it as not just one line, but a collection of lines. So in other words, a slightly more precise way of saying is that the conic cut metric or the conic hull of the cut metric is what is called L1 embeddable. That was what I meant by line type cuts. What it means is that you can represent. So in other words, this is a geometric representation of the graph. See, the graph didn't have a priori any geometric meaning. They were just vertices. But when I looked at the cuts, you got these D's, the distance numbers, and they give you a certain representation, a geometric representation of the graph. If you just had a cut alone, then what it says is that you can just put all the points on a line and cut somewhere in the middle. That's the omega. How you put them is sort of you have flexibility, and how you cut them is the flexibility. So that's like just one-dimensional line embedding representation. Taking a conic combination just means that you don't have to do it in just one line. You don't have to represent the whole graph on just one dimension. You can put them on higher dimension, Euclidean space, but and so in other words, every vertex now has a Euclidean point representation. But the distances between the points, the originally are all L1 distance, because the distance is just this is like an L1 distance because they just add up. Distances in each L1 distance means they add up in each dimension. Take the distances in each dimension and add them up.
So what are the vector representations of the vertices?
Okay. So that depends upon what these d omegas are and what these alpha L's are. So how you represent them is the flexibility in how you choose your cut. So the choice of the cut is the representation. The choice of the cut and the conic combinations are the representation.
At the end you are looking, when you say it is like L1 embeddability, it is like we can find a representation for each vertex such that the norm one of the difference of two vectors is like the distances that they are.
Exactly right. That's exactly what this means. When I say, I had step 1, step 2 somewhere there. So I really, in step 1, I'm trying to look at what a cut means. What are these D's? They're just numbers 0 or 1. I'm trying to get some geometric feel for these numbers. And the geometric feel is that you can represent the vertices of the graph as points on a Euclidean space in such a way that the L1 distance between the points that you embedded correspond to the D values. That's exactly what it is. If you can embed them all on one line, then that gives you a cut, just the cut itself. But this whole point of this conic combination says that, well, you don't have to do it on one line because we are only interested in the min cut, and the min cut is the same as the min conic cut, and so you can have multiple lines and it's still okay. So in other words, you don't have to embed them on one line, you can embed them on sort of higher dimensional Euclidean space, but just count the L1 distance. Okay, so that's the step 1. So line type cut simply means that cuts are metrics that can be embedded in L1. What about the dual of the flow? It's the dual of the flow is out here. Well, there is no such constraint. The D's, the distances, obey the triangle property, so they are like metrics. But there is no constraint that they should be embeddable on L1 or anything like that. They're just open. So now the question is, I guess now that's the issue. So you have a geometric feeling here. In one case, it's an arbitrary metric space. There's no geometric representation. That's the dual of the flow. And in the other case, which is the sparsest cut, you have the same objective function, but constraints on the variables. The variables are the metric points, but they are not arbitrary metrics. They are things that can be embedded in this way. And you get the distances you get in L1 is the one that you should pick, not anything else. How far away are they? So can every metric be nicely L1 embeddable? See, the other thing is that we have an objective function. We don't necessarily have to match the variables exactly. Our objective function is kind of interesting. If you look at this here, the objective function has a numerator and a denominator. The numerator, I don't mind if it contracts. So in other words, I just want to see if that is close to the cut. So if the distance is contracted when I gave an embedding, that was okay. But the denominator should not contract too much because that's going the wrong direction. So you kind of want, so I guess the geometric question is the following. Given a metric, arbitrary metric, can you find an L1 representation of it? Now this is an embedding question. In other words, you want to have a geometric representation to this arbitrary metric space such that you get L1 distances, such that the L1 distances are all contractions from the original metric values, so there are no more. But for certain special points, in fact exactly k of them, SITI, they shouldn't contract too much. In fact, hopefully they shouldn't contract at all. So this is the kind of thing you want, and this turns out is a very well studied topic. Let me erase. This was dirt. So what we are looking for is let me erase this. So that was the conclusion was that you got L1, you got the geometric representation. So what you're looking for really is you start off with the dual of the flow, so it's any metric. You want an L1 representation of this such that, so in other words, you want, I guess you want a representation for every vertex V into, I guess, some high dimension space Rm. You want to map these to real values, and you can call this d tilde as the L1 distances of the points here. So d tilde of u comma v is the L1 distance of psi of u minus psi of v in L1. Okay? So look at this d tilde. So this d tilde is the kind of thing that you get from the cut. This d is what you get from the dual of the flow. So this is, of course, more restrictive than this. And what you really want is that you want d tilde of every edge to be a contraction with respect to the, I guess you start with the optimal value of the flow. You create this. But you also want to make sure that SITI is at least as large as the original value. I don't know, you try to make sure it's at least as alpha large. See, if you didn't have any of this constraint, you can always do an embedding in a trivial way. Because if you just have contraction, then you can just put them all into the same point, and the distances are all 0. So you need some counterbalancing direction. If you just getting a contractive mapping is too simple. So you need to make sure that not all distances shrink. Some interesting distances stay the same, or at least nearly the same. The question is, how large can this alpha be? Or how large can it be? Let me say this. Well, for sure, alpha is larger than 1, but how small can it be? If it's too large, then you might miss the point if it contracts too much. This is a celebrated sort of study topic by itself, and a classical topic in actually maybe applied mathematics now, but at the time mathematics itself. So part of Fields Medal winning work by Bourgain So he showed that in general for so here we have k-specific points, but Bourgain was interested in making sure that this kind of a contraction, this kind of a lower bound is met for all points. And he was able to argue that alpha is actually, I mean, it's exactly tight. In other words, there exist graphs where it can be as bad as log n, and furthermore, it's no more than log n for every graph. So alpha doesn't have to be too large. If it's very, very large, then of course this contraction will just shrink too much. How is this alpha related to for us? Well, the alpha is exactly the gap between the gap in the ratio sense between the dual of the flow and the sparsest cut. Otherwise, the programs are identical. So you just have to convert the objective function from one to the other. And when in the process, you get this factor alpha. This alpha shows up in the denominator as 1 over alpha, and that goes up. So the ratio between the min cut and max flow, or the sparsest cut and max concurrent flow, is this alpha. And that concludes sort of the proof that max flow and min cut are close by. Turns out for if you had just 2 points, k equal to 2, and you wanted to make sure it's contraction everywhere, and except only for 2 specific points you wanted to maintain the distance, you can always do that exactly. And there is a very simple embedding, in fact, in 2-dimensional embedding that you can do. I think we have definitely stepped out of my time. So that's something, I'll share my notes so you can take a look at it. I think it was definitely ambitious to talk of polymetroidal networks too in this talk. You had this question. And its connections to wireless was definitely more ambitious than I had imagined. I'm around, so I'm happy to chat. And I can, I'll give someone asked me for references yesterday, and I think I'll share them all. There are several references for this and also for the polymetroidal work. I'll share them, so hopefully you can also take a look at them.
Any other questions? There were quite a few during the talk. Okay, so I have a few administrative items before we disperse. So first of all, thank you. So first of all, I'd like to read you the picture. We have 3 of our 4 speakers here right now, so we can get a more representative picture. We also have more of the organizing team here than we did on Tuesday. So we can redo the picture. We'll do it the same way. It'll be right outside. It'll be right outside on the stairs leading to the street in Duffield. For evening activities, based on the surveys that we got